My great pleasure to introduce today's speaker, Professor Ursula Molter from University of Buenos Aires in Argentina, who is also director of the Institute of Research in Mathematics, the UBA CONICET, I guess it's called. And today she's going to talk about Riesz basis of exponentials and the Bohr topology. And Ursula, the floor is yours.
Okay, Radu, thank you very much. Thank all the organizers for inviting me. And I found it pretty adequate to talk about this because I'm talking about the work we did with Carlos and Catherine here right after John's birthday party. After his birthday party, we traveled to Canada and we told her about this problem and she got involved. And so this is what I'm gonna talk about today. So I thought it's a nice continuation. I believe it was my last trip before the pandemic. So, so as I say, this was is a joint work with Carlos and Catherine, but we built upon the work of many collaborators. Here is Elona Agora, Jorge Antesana, Carlos and Cabrelli, and Carlos and Diana, sorry, Diana, who in 2 papers set the building blocks for this. However, the inspiration came even earlier by a paper of Sigrid Grepstadt and Nir Leff and Michael Mihail Koluntzakis. So as the title suggests, I'm going to talk about basis of exponentials, and I will rephrase some sentences from the excellent talk we have heard by Alex Yosevich. So the basic question is, given a set B in RD, can we find a discrete set gamma such that the exponentials in gamma are an orthonormal or a Riesz basis for L2 of B? And I use the convention that John taught me to do, and we use the exponentials e to the 2 pi I gamma x for the exponential functions. In the case that this set gamma exists, in this talk, I will call gamma an orthonormal spectrum, or if there is a Riesz basis, I will call it a Riesz spectrum. Obviously, this question can be phrased more general for a bounded, compactly supported Borel measure mu, when there exists a spectrum, either Riesz or orthonormal, for L2 of mu. Well, my clear, where I will focus on is not on the orthogonal case, but since this is something which is the basis, I still wanted to put a couple of slides about this. Immediately when one thinks of orthogonal basis of exponentials, the name of Fugly comes in mind. And in 1974, Fugly posed his famous conjecture that a bounded set omega admits an orthogonal spectrum if and only if omega tiles the plane RD by translations. As Alex told us, in 2003, Terry Tao disproved this conjecture, not in the most general case, but I mean, starting from there, we work on particular cases. It is also true that the conjecture does hold in many cases and has inspired lots of research. I invite you to look at Alex Yosevich's talk. For example, Lava et al. In R proves that it holds for a union of intervals, actually with Yang Wang, a good friend of us. Yosevich and Katz for D equal 2 for convex sets. For D bigger than 3, Lev, Matolsky in 2019. So there is a wide spread of years. And Tao and others proved that it is false in the Z sub P D, where P is a prime. However, it's true in Z2P, as we see in the paper of Yosevich, Mayeli, Azita, who is here, and Pakyanathan in 2017. Well, also Yosevich, Katz, and Pedersen in 2001 proved that if we call B of 0, 1, the ball of radius 1, then L2 of B of 0, 1 does not admit an orthogonal spectrum. So therefore, we already know that there are some sets that do not admit an orthogonal spectrum, independently whether Fugly's conjecture holds or not. So what's the next best thing you can find after an orthogonal basis? Well, we are looking now for Riesz basis. So the question would be, when does a Riesz spectrum exist? And in fact, it is an open problem to find or discover a set omega in RD that does not admit a Riesz spectrum. So far, we do not know if there exists such a set. Some people believe yes, some people believe no. This all can be traced back to a theorem of Landau of 1967, a seminal paper. And he says that if L2 of omega admits a Riesz basis of exponential, I called it E sub gamma, so that you just this E sub gamma, E of gamma is a set of exponentials with coefficients in gamma, then the Berling density of gamma has to be equal to the size of omega, the measure of omega. So if we are looking for a Riesz spectrum, we have to check the density of the set, and the Berling density has to be equal exactly to the measure of the set omega. Kotzma and Nitsan proved that for every finite union of intervals, we can find a Riesz spectrum. They published this for R in 2014 in Invenzione, and for RD in 2015 in the Revista Matematica Iberoamericana. Well, we have by Fugly the conjecture that if a set omega is going to admit an orthogonal spectrum, then it has to tile. So maybe we think that if we want to look for a Riesz basis, we should extend this notion of tiling. And Sigrid Grepstad and Nirlev introduced the concept of Ktile. And they say that if we consider omega in RD, K a natural number, and lambda a lattice in RD, we say that omega is a Ktile for lambda. So the K-tiling property is related to lambda if the translations on lambda of the characteristic function of omega are sum up to K almost every omega in Rd. So it means that every, if I translate omega, a point omega along the whole lattice, it will hit K times the set omega, right? So it will visit the set omega K times. So that's why they coined it to be a K-tile. And one can prove that omega is a K-tile if and only if omega is the disjoint union. I used to denote the disjoint union with a dot inside the union of K sets B1, Bk, and a set Z, where Bi is a set of representatives of, or a fundamental domain of the quotient of Rd divided by lambda, and Z is a set of measure 0. So I will give an example immediately so it's easy to think. Here I'm looking at a 3-tile. So I have the canonical fundamental set, the unit square. The lattice is just Z, Z2, sorry. Then I split the unit set, cube in 4 parts. And this is another set. And I split it in 2 parts, and this is another point. So just that you get an idea of what I mean by a 3-tile. And now I will immediately put a 2-tile. But this one is not bounded, and obviously I cannot draw it, so you have to believe me. So I take the first set is the 0-1 interval. I do it in R. The second set is the 0-1/2 interval, but translated by 1. So what I do is I take the, I will do it here. I take the interval 0-1 and I divide it in the dyadic intervals. And now I translate these intervals. So I take a half here, then I take a quarter, and then an 8, okay? So, and I translate these intervals on the integers, and I will write it down properly. Well, sorry, I didn't write it here, it will come later. So I have an unbounded 2-tile because each of these, the second one, the red one, has all the dyadic intervals just spread out. And this will be a tool that I use a lot. And here I have the first theorem of Sigrid Grebstadt and Nirlev. They proved in 2000 and published it in the Advances in Math. And later, Koulontzakis, I will be more precise what Koulontzakis did. They proved that if a set omega in Rd is bounded and a K-tile for lambda, and the boundary of omega is Riemann integrable, then they can find A1 AK in Rd such that the exponentials of the lattice gamma translated by these fixed vectors are a Riesz basis for L2 of omega. Remember, Omega is a k-tile for lambda. So the translates of any point hit omega. If I translate omega, a point on the lattice lambda, this translates hit omega exactly k times. So lambda has a dual, and this is what I call gamma. And so the exponentials indexed on the sum of ak at gamma plus gamma or minus gamma are a Riesz basis of L2 of omega. Koluntzakis could prove the same theorem, but removing the hypothesis of Riemann integrable boundary. So here we have an example that whenever we have a k-tile, any k-tile will admit this Riesz basis, which I will later call structured. Structured because it's actually the translation of a lattice. Well, reciprocally, in the paper of Agora, Antesana, and Caprelli in 2015 in the Advances in Math, they prove that if we have what they call or coin as a structured Riesz basis, I mean, I have A1, AK in RD, such that this set E sub A gamma, obviously I have to put an A because it will depend on the choice of my K numbers A. And if I have that this set E sub A gamma is a Riesz basis for L2 of omega, then omega is a k-tile. So in some sense, this is a reciprocal or is an equivalent statement if you join both theorems, the one of Grabstadt and Leff and the one of Agora, Antesana, and Cabrelli, you have sort of a Riesz version of Fugly's conjecture, because now you know if we have a k-tile, which is bounded, then we have a Riesz basis. And if we have a Riesz basis of this form, then we have that our set is a k-tile. Well, the problem is that this all holds for bounded sets. What about if our set is not bounded? So here I come back to our original example. And I consider as I told you before in words, here I wrote it down. I have the tile, which is omega, which is going to be a two-tile. It's the union of B1 union B2, and B1 is the 0, 1, and B2 is all these dyadic intervals spread out along the whole real line. In each interval, I have that I translate one of the dyadic intervals into that interval. Okay? So this is a two-tile, which is obviously non-bounded. So we cannot apply Grabstadt and Leff. And one would hope that maybe this set, which seems to be pretty simple, does have a Riesz basis, or a Riesz basis, a structured Riesz basis. The general question, I don't know, but I can ask myself whether this set has a structured Riesz basis. And the answer is no. And why? Because we can prove that for any choice of A1 and A2 in R, there will not exist a Riesz basis of the form E of A1 plus Z, A2 plus Z. And why is this true? Again, by a very fundamental theorem of Agora and Antesana and Cabrelli. Jorge is actually also here in the talk, which is very nice. They prove an equivalent condition for when something is a structure Riesz basis. And they prove that if we have A1, AK in RD, then the set of exponentials which translate a lattice lambda star along the fixed vectors A1, AK, this will be a Riesz basis for L2 of omega if and only if the determinant of this matrix here is bounded away from 0. I'm sorry that I didn't write this theorem in its full, it's not complete because I'm assuming that omega is a Ktile for the lattice lambda. So I start with a set omega, which is a lattice lambda. Like in our previous example, we have the set, which is a 2-tile. So if I want this to have a Riesz basis, I have to find A1 and A2 in this case, such that this is bounded away from 0. Well, I wrote the theorem up here again. So we need that this holds for every omega in P. So even though it's a very clear stated condition, you have to check it for every omega in P. And P is what we call a fundamental domain of the lattice. So we recall that if a set is a Ktile, we have exactly K elements lambda, which translate this set, this omega, a given particular omega, into omega. I'm very bad. I should have chosen different letters. This is a small omega, and this is a big omega. So for any omega, small omega in P, I take lambda, all the lambdas, which translate this little omega of P into the big omega. And since I know they are going to be for almost all omegas, there are going to be K, I give them the name lambda 1 to lambda K, and this is how this matrix comes. Okay, so I take any A1, AK, and I take the exponentials e to the 2 pi I a lambda of omega. Okay, so we have the matrix. It's a little bit technical, but I just wanted to show, I think I'm allowed to do one little proof. And here I will prove that for this particular set here, this matrix will never be invertible. Because look, for the first lambda is for any omega 0, because it's the 0, 1 is the first element of the tile. And then the next element is, well, one of this set B2. So when I make this matrix, I get a matrix which is a little bit easier to look at. And even though I didn't write it very properly, here is a 1, 1 in the first row. And then I have the exponential A1 lambda 2 and A2 lambda 2, because lambda 1 doesn't exist. So I factor out the exponential A1 lambda 2, and I am remaining with this exponential. And for this matrix to be invertible for almost every omega, I need that this guy here is not 1, right? Because if it's 1, obviously this matrix is not invertible. But if you look at my set, every time that I'm in I1, the difference between A2 and A1 is exactly an integer. So I have that this will be 1 for every omega in I sub k, and this matrix can never be bounded away for all or almost all omega. So I just said it and I wrote it down here. So obviously this depends on who is A2 minus A1, right? So I just wrote here the proof. The proof is in the paper that you can read by Agora, Antesana, and Carlos. And it is based that if my difference A2 minus A1 is rational, then obviously being in these dyadic intervals, multiplying with Q large enough will give you an integer. And if it's not rational, then I will have a sequence, since these are dense, which will make nj times A2 minus A1 tend to 0, mod 1. And so for n big, the determinant of this matrix becomes as small as I want. So I can never get that this matrix is bounded away from 0 for almost all omega. So this is an example of a two-tile which is unbounded and where I cannot find a structured Riesz spaces. Open question: does there exist a Riesz spaces for this two-tile? I don't know. Okay, so what we want to do is look, and this is what I am going to talk about today. Still, I come with some older stuff. We will look for conditions on our set omega. Obviously, if it's bounded, we already know that there exists A1, AK. Sigrid and Neer proved that in 2014. So obviously, we are seeking for something that is not bounded, and we want to see when we can guarantee that this matrix, the determinant of this matrix, is bounded away from C. Note that this is a condition which is very strong, because you should prove it for every omega and for every A, set A, right? Okay. So looking at the paper of Agora, Antesana, and Cabrelli, Diana Carvajal and Carlos in 2018 could prove when it can give us a sufficient necessary condition for when the set omega will admit a k-type. Sorry for this, I always mess up with necessary and sufficient. So they prove that if I have a set in RD that has finite measure, we don't require that it's bounded. and is a K-tile, which is what they coin as admissible, then there exists A1, AK such that the determinant is bigger than 0. So what is the advantage? Instead of checking that this determinant is bigger than 0, I have to only check whether the set is admissible. Well, the definition of admissible is the following. Recall that this matrix here is made up of exponentials, which have in their exponent the vectors A1, AK times plus elements of the lattice. So what do? I check whether for my omega in my fundamental domain, if I look at the K translates that put this omega inside my big omega, then I want to ask that these scalar products are all different for a given n. So what it is, they say, if you can find an n such that these scalar products are all different for every choice of omega, then they can show that there exists a structured respaces. So this is now a condition which is not depending on A. You see, I can, in this part here, I had a condition which I had to check for each omega and each A. Here, they give me a condition which I only have to check for each omega. Okay, so it's a huge advantage. They always guarantee that if these guys are different from n, different mod n, for any n could be very large, but the catch is for all they have different. And in that case, they will have structured respaces. So, well, we were talking to Catherine, and the point is that we told her that we were very unhappy that this condition was only sufficient again, because in the same paper, Diana and Carlos exhibit an example of a two-tile which admits a respaces, but is not admissible. So the condition of admissibility is not sufficient. And then we... Yes? Okay. So, I'm sorry. So they prove that the condition, well, sorry, I did again say it always wrong. So the condition is only sufficient. So if the set is admissible, then I have the respaces. If I have a respaces, the set is not necessarily admissible. I think I said it right, but I used the wrong word, like I always do. Sorry. So the idea, and I won't go into this because I don't want to go over my time, is that instead of taking in the original example every interval and putting there one of the dyadic intervals, I use the Kronecker approximation theorem that says that if you have A1 and A2 and R, which are Q linearly independent together with 1, Then for each j, they are linearly independent, q linearly independent. Note that q is here important because so we don't get an integer. We are not able to get an integer when we make the product. And so what happens by the Kronecker approximation theorem is that you can get as close as you want to any two q linearly independent numbers, so that this norm here is little. So I make a set which I is now which will have that the determinant of this matrix is big for small, is big, but is not admissible. It's not admissible. And this is the point which I wanted to make. Since I still take integers times my numbers, I will end up with having two numbers which have the same, which are different modulus n for any n which I pick. I guess this example was a little bit too technical, but the point that I want to make is that the admissibility condition is only sufficient and not necessary. So when we joined up with Catherine, we looked at this picture. We have bounded K-tiles for which Sigrid Grepstad and Nirlev proved that and Kolunsakis proved that there always exist structured Riesz spaces. So then we have the admissible K-tiles, because these sets don't have to be bounded anymore. So they are more. And then there are K-tiles with structured Riesz spaces. I didn't tell you, but maybe many of you already figured out that any bounded K-tile is necessarily admissible, because since it's inside the ball, if I take the ball sufficiently large, the translates will all be smaller than n. So if I take a number n, which is much larger than the radius of the bound of the ball or the cube, then obviously if I translate on that one, it will be this, they will all be different. So bounded K-tiles are special cases of admissible K-tiles, but now with our counterexample, we show that they show that there can be K-tiles with structured Riesz spaces which are not admissible. Well, and this is what we wanted to do, is we wanted to find a necessary and sufficient condition for a multi-tile omega, big omega, to admit a structured Riesz spaces of exponentials. So we looked at the counterexamples. The first one was much easier to explain. The second one is a little bit more complicated, but we always found the same. And here the great thing, this is what I always ponder about a collaboration. We joined up with an abstract harmonic analyst like Catherine. And so she said, well, this looks all very related to something which is called the Bohr topology, which for many of you is very familiar. And it turned out that that gave us a necessary and sufficient condition. I will not do the proofs, but I will tell you what we did. So I used the Bohr compactification. We used the Bohr compactification. And I just want to recall for those of you who don't remember, like I did when we talked with Catherine. So I start with a locally compact abelian Hausdorff group. We take its dual. So every group has its dual. But the group is not necessarily compact, because if it were compact, I already have it compact. So I'm looking at something which is not compact. So what do? I have its dual, called the Pontryagin dual. And now I give this dual group the discrete topology. Yes. So this is something you can do. You have the same set and you give it two different topologies. The first one is the one induced by G, which is the compact open topology. But the second one, I just give it the discrete topology. And now I take the dual of this guy, of the discrete guy. And what is the dual of a discrete group? A compact group. And this is the compactification of G, the Bohr compactification of G. And the only thing I will need of this, and obviously I needed more, but I think to give the talk, I wanted to introduce what are the neighborhoods of a point x0 in my compactified group G. Well, and these are called n x0 k e epsilon. So the neighborhood of size epsilon associated to a compact set in the discrete group gamma d are all those x's in the compactification, such that when I look at the characters in K, the absolute value between X acting on the character and X not acting on the character is smaller than epsilon. Obviously, there is the big pi here, is since the only compact sets in the discrete topology are finite elements, what turns out that all the basic neighborhoods of the compactification of G are simply all those X such that when they act on a finite number of characters, their distance from this action between X of gamma I and X naught of gamma I is smaller than epsilon. And this is what came handy to us. So we started with a set omega, which is a Ktile for a lattice lambda. The measure of omega is finite, but the set is not bounded, not necessarily. Obviously, we look at the non-bounded ones because the other ones are admissible and are already taken care of. And we call, as before, this lambda sub omega, the elements of my lattice lambda, such that the translates of the omega fall inside of the big omega. Now I look at the Bohr compactification of my lattice lambda, and I've built the following matrix, which is a matrix which is only related to characters in the compactification of lambda to the k and any elements a1, ak in Rd, which is to make the matrix, let the character act, he sub I act on aj. So in the particular case that these characters are the ones of the lambda, which are the translates that send the little omega into the big omega, this matrix is nobody else than the one defined by Antesana, Agora, and Cabrelli, which is the one that has to be bounded away from zero, whose determinant, I'm sorry, has to be bounded away from zero. And so, I just said this. So what I do is I look, given a k tuple, so here I should write A1 up to a k tuple in RD, I look at all the characters in lambda, in the compactification of lambda, such that this determinant is zero. So given any k vectors, A1, AK, I look at which elements of lambda, the compactification, makes this matrix have determinant zero. And now I look at the set D, which is all the translates which take an element of little omega inside the big omega. So I know that there are k for almost every omega. And so I close this set, closing in the compact topology in the compactification of lambda tilde to the k, and I have my theorem. We can prove that it is equivalent for any set A1, AK in RD, that the set that is the translation of the dual lattice of the one that gives me a Ktile by AJ. So this set EA lambda star is a Riesz basis, a Riesz spectrum, or in other words, these form a Riesz basis for L2 of omega, if and only if the closure of D, I mean, the closure of the translates that take my omega inside the big omega, and none of the elements in the closure can annihilate the matrix MA. So you can ask yourself whether this is any help, whether for finding conditions to determine if a set omega has or doesn't have a structured Riesz basis. Well, there is sorry, I said this. There is a nice corollary, which is in the case for k equal 2 necessary and sufficient. In the case in general, it's just sufficient, but a Ktile has a structured Riesz basis if there exists an A such that the closure of the differences of those lambdas that make that my set translated into the big omega and the annihilator of A is empty. So I just want to look short at the example. Remember that in this example of Carvajal and Cabrelli, which admitted a Riesz spaces, but was not admissible, right? This was one of our problems. The set lambda omega is simply 0 and j times mj, where j and mj are those that make the a1 and a2, the exponentials in a1 and a2 being close. So the set of differences of lambda omega is simply plus minus j mj. So if I have an element beta different from 0, and I have a very small epsilon, then the Bohr closure of Y misses the annihilator of A, where A is just the difference A2 minus A1, and beta was just an irrational, which I picked such that the matrix E, well, I should write, E beta omega, the determinant of this matrix, was bigger than a number. Sorry, not omega. E beta, how did I know that? Lambda, no? And so this set, which was not admissible, but which did admit a structured Riesz spaces, satisfies our necessary condition that it misses the annihilator of A. And I will close here. Thank you very much. And I have here the references. And I think there are some missing, but if you have, you can write to me and ask me more questions.
Great.